Hello, my name is Cliff Goldstein. I'm with Eclipse Engineering. We're a manufacturer of seals and different types of polymer profiles. Today we're going to have a discussion on rubber energized seals, but we're going to start with some basics. We're going to basically cover how seals perform, what it takes to do seals, and we're going to end up with rubber energized elements like urethane or PTFE or Teflon. A little background: Eclipse Engineering, we design and manufacture high performance polymers. We make a variety of different types of seals, specifically rubber energized seals, spring energized seals, and rotary seals. And today our focus, as we've stated, is going to be around how rubber energized seals work. So the first thing that we want to discuss is some seal considerations. And whenever we go into the design process, we ask ourselves, what are the criteria that are going to decide what a seal is going to look like? So I start off with cost being number one, because if we're into the automotive industry, typically these seals are low cost, and we've got to find a way to keep our dollars down. We look at things like the pressure, the system pressure, the types of fluids that are involved, the exterior environment. In other words, are we going to be operating in very cold temperatures or very hot temperatures? So temperature has a great big impact, or a large impact. Friction is another area. Is friction important in the application? And to what level is friction important? Finally, again, I've mentioned briefly before, but fluids are important. Are we going to be sealing gas or a liquid? And will that fluid remain at one viscosity, or will it be changing viscosities? And finally, if you'll notice on the slide, there's two signs there that say cost. And oftentimes, we'll start off a lot of our discussions with engineers, and cost is no factor, but we know that cost always enters into the formula. I always like to start off with what the perfect weld joint is, and if we could weld all of our joints together, we'd have perfect seals. But in reality, even a welded joint has a certain level of porosity, and so we need to make a determination as to what we consider an acceptable level of leakage, because no seal will have a zero level of leakage. Even that welded joint will have a level of porosity. So we look at these different weldments. I showed you a butt weld to begin with, and now I'm showing you two faces coming together. And we're going to move from here in just a second. But these weld joints are typically tested with helium leak down tests. And in a lot of applications where we're sealing a gas, helium is often used as a method of determining what the level of leakage, level of acceptable leakage is, because we know that there are no perfect seal joints. Going forward, a very common type of seal is a gasket, and these gasket materials can range in a variety of different materials. Some of the original gaskets were, of course, cork. There's paper gaskets. There's complex gaskets that are made out of metal. So we have metal C-rings, or even soft metallic elements can be like a brass or a bronze can be used as a crush gasket in certain environments. So gaskets take on a lot of different forms, but one of the simplest gaskets is, of course, that does a good job, is an O-ring. And the nice part about an O-ring is that it has some resilience. So when you install an O-ring into one of these face seal joints, there is a level of tolerance so that when the two faces come together, we can, with the proper amount of clearance, knowing what kind of pressure we have, an O-ring does an excellent job of sealing. And for all practical purposes, excluding things like gaskets, like what you have on a valve cover or on a head gasket, O-ring is a pretty common static type of seal, and depending on the pressure, it might be an O-ring, it might be an O-ring with a backup ring. And what I'm showing now is an O-ring with a backup ring. And if we go back to the previous slide, if our pressures typically are under about 1,500 psi, an O-ring without a backup ring is a very common way of sealing a static joint. Similarly, when our pressures exceed 1,500 psi or our extrusion gaps begin to get rather large, we'll use a backup ring to help to retain the O-ring. Now, the purpose of that backup ring is so that when the system is pressurized or energized with a fluid, the O-ring will drive into the backup ring and force the backup ring into the extrusion gap. Without an extrusion gap, without a backup ring, typically an O-ring will nibble or deteriorate in that joint. You can't really go forward too much further in rubber energized seals without having a little bit of an understanding of what these O-rings look like. This is a page out of the Parker O-ring book. This is a pretty standard page, and what it has in it is the standard cross sections for O-rings, and there's 5 standard cross sections going from 0 series to 400 series, and in this table it actually shows what the glands would look like. And so when we're doing design work with just O-rings, or even designs with O-ring energized Teflon seals, we'll use these types of interferences and make sure that we have enough gland clearance so that we don't distort or cause the O-ring to have a premature failure. An O-ring energized Teflon element relies on both elements to continue to perform. And so even though the O-ring is static, it's moving around in the joint. If we don't give it enough room due to temperature or pressure considerations, we can prematurely fail the O-ring, which will fail the O-ring energized Teflon seals prematurely. You'll notice that there's a couple of important lines in here. One is the L gland depth, and that tells us in static seals what those glands ought to look like for gland depth. And of course groove width, and that's to make sure that the seal has enough clearance inside the groove. Now this particular chart also has a 1 backup ring and a 2 backup ring groove width, and we use those when, with multiple backup rings to make sure or to ensure that we do have the proper clearance for the O-ring in the groove. And just as an initial discussion, one of the items that we talked about early on was friction. And this is another page out of the Parker O-ring book, and it gives the force per inch of the different O-rings under different levels of squeeze and different durometers of O-rings. So lower durometer O-rings produce less force, higher durometers, correspondingly give higher force, and depending on how much squeeze we put on the O-ring will determine how much load per inch that an elastomer will provide in sealing, both as a dynamic seal or as a static seal under a Teflon element. So when we're calculating friction underneath the Teflon seal, or calculating friction with a Teflon seal, we use these charts to tell us that under 0 pressure, how much load is being generated just from the elastomer. The other component when calculating friction will be the actual fluid operating on the seal cross section. So we use both those components when determining how much friction a seal is generating. That and the combination of the coefficient of friction of the raw material determines how much drag will be on that system, whether it's rotary or whether it's reciprocating. Couple different types of elastomers. We know what an O-ring looks like, but there's an X-ring, or another name for it is quad ring. They typically are doing a little better job at sealing in dynamic situations. They're good bidirectional seals, easy to install, just like an O-ring. They're relatively low cost, and they do come in a variety of materials, but not nearly the variety that the elastomers do. Chemical compatibility is limited to the type of rubber that we're using. We like to think of them as slow, dynamic, and generating high friction. And typically, we reduce the compression on elastomers in dynamic loading so that we don't drive the friction up. But of course, when we do that, we also increase the level of leakage that's tolerant underneath that elastomer element. Temperature ranges, depending on the compounds, can be as much as that. The slide says 350 in the fluorocarbons or Viton type elastomers. They'll go to as high as 4 with extrusions to 500 degrees Fahrenheit. And of course, at low temperature, there's some custom compounded nitriles that will get you down into the minus 65 range. But in quad ring style, that's a very expensive process because those are special run seals. You have limited shelf life with all elastomer products. The U-cup seal is a moderately cost element. It is pressure actuated. There's a lot of common sizes that are on the shelf. It's well suited to reciprocating applications, and they're easy to install. Usually they're made out of urethane materials, but they can be made out of elastomer materials like the different nitriles or whatever type of rubber compounds you'd like to have them manufactured out of. Again, chemical resistance is an issue. They're not suited for high PV or in rotary applications. They do have limited temperature ranges, and of course, the U-cups are unidirectional. And the next style of U-cup seal out of rubber elements is an O-ring energized U-cup. And in this particular case, what it does is it just simply increases the loading of the lip. And typically, this is done at low pressure to get low pressure sealability. However, they are found in high pressure applications. Generally, at high pressure, the fluid will do the sealing, but at low pressure, that O-ring creates an awful lot of drag, but also does improves the sealability at low pressure. So we're gonna move on now to rubber energized PTFE or Teflon or whatever type of material we want to machine it out of, but basically rubber energized polymer elements. And what I'm showing here is a very basic design. This is what we call a channel seal. It's one of the most basic Teflon element style seals that's available in the marketplace today. These types of elements will retrofit into standard O-ring grooves. And so if you've got an O-ring in a groove and you want to reduce the friction or you want to extend the life of that product, the channel seals will retrofit into either 0, 1, or 2 backup ring grooves. It obviously brings the friction way down because that PTFE element or whatever material we make it out of can have a coefficient of friction from anywhere as low as 0.04 up to about 0.12 if it's a PTFE element. And if we're getting up into some of the urethanes, we can get closer to 0.5 or so on friction. Where that rubber element will have a coefficient of friction of about 1. So it's dramatically less than that rubber element. so it reduces friction. It extends the life of the O-ring. There's an ease of installation. They're fairly easy to install. Generally on rod seals, we kidney shape them. On piston seals, they can be stretched out and then resized back into shape. So they are fairly easy to install. They do have a finite life, though. So if there's a lot of motion or high motion, we can wear that cap out. They are a little bit fragile on installation because they are very thin. Try and limit the fillers or the amount of filler in those seals because of the thinness of them. However, and they do have a little bit lower extrusion resistance compared to some of the other types of elements. A PTFE cap seal, we're going to talk about that next. These do not fit into standard O-ring grooves. However, it provides a much greater performance over the typical channel seal. That O-ring becomes far more important here because we need that O-ring to support the Teflon element. We build in interference in these cap seals, and what the O-ring does is it helps to maintain that interference, especially on startup. These types of cap seals have increased extrusion resistance over other elements because it puts more PTFE or more element, more material into the extrusion gap. Lower friction over the O-ring, of course. We have that same friction level of 0.04 to 0.12 and a much greater dynamic range. So this will handle quite high speeds or PVs compared to other types of sealing elements. They can be used both in rotary and reciprocating service. It's available in a multitude of compounds, and we'll talk about materials later on in the presentation, but some materials are better suited for different types of mating shaft materials, and so we try and make materials based on what we're sealing against and also the kinds of fluids we're running in. They are machined, so we can customize them based on the customer's gland. This particular seal is a bidirectional seal. It will take pressure in both directions. Some of the disadvantages, we do have limited service life from the O-ring, but it's operating as a static seal, so it's not nearly as important as just an O-ring operating without any type of cap at all. A little better surface finish is required, and the reason for that is that Teflon will ride over bumps that are in the that are on the sealing surface that we're trying to seal, where an O-ring has a tendency to follow the shaft or the bore material a little bit better. They require additional hardware design like split glands or retaining plates. But in general, these cap seals are easy to install. They can be kidney beamed to go into rod glands, or they can be easily stretched and reformed using resizing tools to get them to go back in for piston-style seals. This is a picture, a cross-section of a seal, and I put this up here so that as a customer or as your customer looks at these seals, they get an understanding that what we do is we always try and depict things in a cross-section. And I'm showing standard gland dimensions or how our seals are depicted. You can see that we show, in this case, this is a piston-style seal. So there's a bore diameter, a rod diameter. You'll notice that the surface finish on the dynamic surface is better than the surface finish in the gland. And also we call out radiuses in the bottom of the groove. And we need radiuses specifically because there's the customer, when he's machining these glands, typically can't make sharp corners. So we do build in radiuses for the ease of machining. We also show the groove width. Now you'll notice that the groove width typically will be at least 5 to 10 thousandths wider than the actual PTFE element, and certainly much wider than the elastomer. The elastomer gets deformed. You notice that it turns into an oval shape when it gets into the groove. That's the initial squeeze that is on the ring. In this particular picture, we're also showing some installation or some inspection dimensions, so that when a customer receives this part, we're showing the diameter of the ring in the uninstalled state, as well as the width of the seal, and also calling out the elastomer. And sometimes we'll call out the dash size of the elastomer. We're also calling out the material. In this case, it's a polyimide filled PTFE, or this ET014. The buffer ring will handle very high pressures. It's relatively easy to install. It provides nearly zero leakage, and will allow fluid to return back into the system when the rod is returned back into the system. It is not a zero leak seal, so it needs a secondary seal behind it. Typically, buffer rings will either have dual buffer rings and they could be out of PTFE elements, but generally we'll find the second element not to be PTFE, but to be some other type of elastomeric material, like a urethane or some other elastomer material. And what that does is it will provide a zero leak seal on the backside, and the in between the buffer ring and that secondary seal, there'll be a little bit of fluid which will keep the secondary seal lubricated. The trick to making this seal work is that the pressure in between the buffer ring and that secondary seal will be somewhere less than 100 psi. So that causes that secondary seal to perform for a very, very long time. Buffer rings like this will operate at 3,000, and with backup ring systems will operate at much higher pressures into 5,000 and 10,000 psi. Very high PV rates or very high cycle rates. So it's a pretty reliable system. They're found a lot in construction equipments, but these are rod seals. I've seen them on pistons, but typically people use them to create a zero leak rod seal system. It is unidirectional, so it has to be installed properly, and typically it's found with some type of oil or some type of hydraulic fluid, or some kind of combination of water-based fluid. This is a cross-section of what it looks like, and you'll notice that it has a unique design. That angle on the back side, the purpose of that is that when the rod is being returned into the system, in this particular picture, the seal would actually rotate counterclockwise slightly in the groove, allowing fluid to come back underneath the lip and into the system. It is energized with an O-ring, and in some cases we can energize them with square rings, which increases the load and does even a better job of sealing it at various pressures. We're going to move on now to rotary seals, and rotary seals are kind of a different animal because one of the things that we have to be concerned with is heat. Heat is probably the biggest reason why rotary seals fail. Also, with rubber energized rotary style seals, one of the primary goals is to ensure that the O-ring does not rotate in the groove. And we have some special ways of taking care of that. So we're going to talk about this a little bit. You'll find rotary seals like this in things like rotary unions, and a rotary union would be described as a device that would fit, say, in the center section of a backhoe or a shovel, where it's rotating around the center. The top section of the machine rotates around the bottom section, and fluid has to pass through a joint. They're generally very slow turning. You'll notice generally 10 to 15 RPMs is about as fast as they ever go. The typical seal in the past has always been just O-rings, but they have had high failure rates just due to the pressure and pressing on the elastomer and pushing into the extrusion gap. the Teflon energized or rubber energized Teflon seals do much better in these rotary designs. One of the problems with the design is that as these are rotating, oftentimes the elastomer wants to rotate underneath the Teflon element. And if that happens, oftentimes we'll break the elastomer. So we have a process where we treat the PTFE and put a chemical on the back side of it. And when the rubber and the Teflon element are put together in these rotary joints, it causes mechanical bond to occur between the rubber element and the coating that's applied to the back side of the Teflon, and which causes the friction to be increased dramatically between those two elements, so that we can drive all of the rotary action at the dynamic surface. The disadvantages of this are that putting that coating does require a little more time. We have to etch the Teflon and then, of course, apply the coating. O-rings have a limited service life, and that's in all applications. We do, of course, require a better surface finish for the PTFE or Teflon element. And in these rotary unions, we typically don't have split hardware, but it is limited to speed. If we get going too fast, even that element, even the coating does not stop it from rotating. When we're looking at seals for customers, we always have to evaluate the cost in the process of putting these seals in. And so when we design or develop seals, we always try and start off with, will an O-ring do the job? And that's the way you should look at seals when you're putting them in customers' hardware. Putting in seals that are very expensive and are not necessary doesn't really solve the customer's problem, and then you drive the cost up of his hardware, and especially if an O-ring will do the job. So we always start off when we're faced with an application, we ask ourselves, what's the least expensive, most effective seal without giving up performance? And so we look at O-rings. So in static lands, we typically find O-rings. If it's not too dynamic, we'll use quad rings or X rings. U-cups are a standard seal. You'll find them, everywhere in the marketplace. Radial lip seals fit in there, and then we get into the higher performance materials like the cap seal or the buffer ring. These types of PTFE O-ring energized style seals, and they're certainly higher cost than most of these others. Finally, we move into spring energized seals where the costs are getting even greater, and then rotary cased spring energized seals and rotary seals, and finally, what's not shown there are mechanical seals. So when we look at a customer's application, we consider these elements as we're going up the decision tree as to what direction we should be going for the style of seal. I don't think that we should ever give up performance, but if an O-ring will give the same performance as a rubber energized Teflon seal, we should just be putting an O-ring in. But if friction is of a concern, these other seals aren't going to cut it. We'll end up putting in something like a rubber energized or even a spring energized seal, depending on what the customer's requirements are. Another consideration in the design is PV, or pressure velocity. Pressure velocity is simply multiplying two numbers together, pressure in PSI and velocity in feet per minute. Most of the materials that we use for sealing have limits to what those numbers are. There's some Teflon elements that will go up to 500,000 PV, where most elastomers are much, much lower than that. So, and it's irrelevant of whether it's reciprocating or rotary. PV comes into play. If you exceed the PV limits of the mating materials, they will fail prematurely, so we need to be very cognizant of that as we're in the design phase of selecting a seal for a customer. The examples here are how to calculate PV. I'm not going to go through them, but it's a very simple calculation. But PV is very important, and these numbers, PV limits, are available for all materials that we use for sealing. This is a seal selection chart, and it helps you to or guides you through selecting the kind of seal you're looking for. And you'll notice that rotary motion, you'll see PV is greater than 100,000. That we use some special items to keep the seal stationary. But for rubber lip seals, you'll notice that we need to keep the PVs much lower, or else we'll begin to spin in the hardware. So we're trying to we use these to help us decide what the seal is actually going to look like. Considerations are, of course, pressure, temperature, fluids. So even though we have PV, we need to throw in all these other factors. And we have to remember that as we move quickly, or as the hardware is moving faster and faster, we generate more heat. That's not really a consideration in PV, but if we drive a lot of heat into the system, we will cause the seal to prematurely fail, even though we didn't exceed the PV, because these PV limits are done at room temperature around 70 degrees Fahrenheit. I'm going to switch gears on you a little bit. One of the elements that is found in all piston and rod type seals are bearings. Bearings are crucial to allowing seals to perform properly. If we can't keep the hardware centered, if we can't keep the rod centered in the rod gland, or the piston centered in the bore, we're asking the seal to perform these functions. Somehow or other we have to guide these elements, and so we'll make different types of rod or piston wear rings. This one here is depicted as a rod wear ring. They can be made out of a lot of different materials. For low loads, or where there's not a lot of side loading, PTFE or filled PTFE elements work great. When the loading gets very, very high, we have some polyester materials that can handle loads as much as 50 times higher than what the PTFE elements will handle. I'm going to bring up an application for a wear ring. And here's a case where we had a wear ring in an application that was out of PEEK, which is also a wear ring type material. However, this is where material becomes very, very important. The material was wearing the rod out. It was pharmaceutical, so there was powder getting underneath the PEEK, and those two materials were becoming very abrasive on stainless steel rods. In this particular customer's case, these rods were 8 feet long and 4 inches in diameter. We came back and replaced it with a polyimide-filled PTFE split bearing. We solved the wear on the shaft, and even though the loading of the Teflon element didn't handle nearly as well as the PEEK, in this particular application, the PTFE elements were more than sufficient to take care of the load at a lower cost to the customer without having to replace an 8-foot-long stainless steel shaft. So materials are very, very important. This is a piston seal bearing assembly, and you can see that I'm depicting 2 bearings on both sides of a piston style seal that's O-ring energized. The purpose of the bearings, as I described before, is to keep that piston centered in the bore. Depending on the diameters, we may do it with 1 bearing, or we may do it with 2, or depending on how bad or how much loading we have, we may use a combination of bearings. If we split bearings, as we're seeing in this picture here, what we're doing is we're not putting all the loading on one side. We basically keep the piston balanced in the bore. With very short pistons, that's not available, but if we can split the bearings, we're better off because we keep we don't allow that piston to rock inside the bore. This is a typical rod sealing application, and we talked about the dual elements. You're looking at a dual buffer rings in this particular case. The fluid is coming from the right side of the picture, and the fluid is then energizing the buffer rings. You notice that we put a bearing in between the two buffer rings. That bearing will be lubricated because we know that the first seal will leak a little bit. The second seal being either some kind of elastomer type element or even a U-cup will be the mop-up or the zero leak element. Pressure in between the two seals will be roughly 100 psi. In this particular application, you'll notice that there's another bearing behind the second buffer ring or behind the second U-cup, and the purpose of that bearing, again, is to help stabilize the rod. There's a third element in there. We're not going to talk a lot about it, but it's a wiper. Wipers are critical, especially in dirty applications. Couple of the features that'll wear a seal out very quickly, of course, are friction and heat, but dirt is also another large contributor to the failure of sealing elements. And so we try and keep the level of dirt out of these systems using wipers. And finally, this is just a cross-section of the two seals in place, which creates a near-zero leak system. That second element, oftentimes customers will just have a urethane U-cup, but under high load, that urethane U-cup with high cycle rate and high pressure, 3,000 psi, 2,500, 3,000 psi, that urethane U-cup will typically wear out rather quickly. When we put the buffer element in front of it, we extend the life of that U-cup to at least as long as that PTFE or that buffering, the Teflon element. We've extended the life of the urethane elements by 3 and 4 times its standard life by putting that PTFE element in front of it. Finally, these are rod scrapers. I talked about it briefly. Rod scrapers are used to keep dirt out of a system. It's important to keep the dirt out. I mentioned it earlier. And there's a lot of different varieties of how we make these rod wipers, but they are important in keeping the system clean. This is just one version. There's probably a half a dozen versions that we use depending on the customer's hardware and the type of dirt we're trying to exclude and how much loading we can put onto the shaft. Again, all of these elements create friction, and so we need to be very careful about what kind of elements we're putting in. Lots of different materials to work from. This is I'll call this the short list, and you'll notice up on top is PTFE or Teflon. We do use some virgin grades, but typically we fill PTFE with a variety of materials, things like carbon, graphite, polyimides, bronze, stainless steel. There's also different types of PTFEs that we can use that have better strength characteristics, like TFM, which is a copolymer, or PFA, which is an injection moldable PTFE. Some of the other materials we use for backup rings, things like PEEK or nylon or Delrin, acetals. Urethanes, of course, are good secondary seals. Briefly, the rubbers are out of a variety of materials, which I'm not going to cover here today. UHMW is another common material, although not used as much in hydraulic systems, but in air systems. UHMW is an excellent seal material. Hytrel or thermoplastic elastomers. For low temperature, we have PCTFE. PVC is normally used for installation tools. Some high temperature materials like Torlon, Altem, Riton is a good bearing material. I mentioned polyimide or Vespel as a filler as well as out of a seal material. Material that we've never used is Solazol, but it's available. I talked about high load bearing materials. That would be a polyester resin fabric composite, which is capable of 50,000 psi loading, where Teflon has about 1,000 psi. These are bearing grade type materials. And then finally, just carbon face seals, this sort of thing. That ends the presentation. If you have questions, please feel free to contact your local distributor, or of course you can contact Eclipse Engineering. And thank you very much for listening.